Bonjour à tous et à toutes. Nous allons avoir le plaisir d'écouter aujourd'hui la soutenance de thèse de Raphaël Wicker, dont le titre en français est « Baryons dans les amas de galaxies, effets astrophysiques et contraintes cosmologiques ». Le jury ici présent et à distance est composé de Madame Veronica Strazzulo à distance, Monsieur Stefano Ettori à ma gauche, Monsieur Dominique Eckert à ma droite et Monsieur Joren Beller à distance également. Nous avons sur la droite là-bas les membres de l'équipe de direction de la thèse et moi-même je suis Karine Boccanini qui ai l'honneur de présider ce jury. Raphaël, tu as 45 à 50 minutes pour présenter ton travail en anglais.
Yes. So, hello everyone, and thank you very much for being here today. I'm Raphaël Wicker, and in the next 45 minutes or so, I'm going to discuss the work I've been doing for the past 3 years under the supervision of Marian Douspis, Salvati and Nabila Aghanim, on the study of baryons in galaxy clusters, the study of the astrophysical effects, and cosmological constraints. The presentation is going to go as follows. First, a short introduction about large-scale structure in galaxy clusters. Then I'm going to present my projects on the study of the hydrostatic mass bias from the gas mass fraction of galaxy clusters, the study of the structure of multiple cluster systems, and then I'll wrap up shortly in a conclusion. So first, I would like to come back to the basics and give you a bit of context on a brief history of the universe, which started as a very homogeneous medium, and throughout its history and expansion, started to structure itself up to very recent time. And this structured universe at late time is the one I've been interested in for the past 3 years. So I first discuss a bit how this structure formed, and in a very simplified view, from small primordial density inhomogeneities, which can be detected in a cosmic microwave background. And from these density inhomogeneities, under the effect of gravity, they started to collapse to form the very first smallest structures from the first galaxies, which, again, under the effect of gravity, started to collapse to form larger and larger galaxies, which collapsed in the end inside this structure at the larger scale, a complex pattern, which is called the cosmic web, which can be seen both in observation and in simulations, which is a complex pattern composed of several environments like galaxy walls, some underdense regions, which are called cosmic voids, some filaments, and at the junction of these filaments, nodes, overdense region of the cosmic web. And inside these nodes are what I'm going to be interested in today, galaxy clusters and groups of galaxy clusters or multiple systems. As the most dense regions of the cosmic web, galaxy clusters are also considered to be the most massive gravitationally bound structures of the universe. I'm sure that's a sentence you already heard. And they are quite interesting to investigate, notably because of their matter content, which is roughly similar to the matter content in the universe. First, more than 80% of dark matter, which can be detected only indirectly via gravitational lensing effects. And then gas and galaxies, which together form what we call baryons, this ordinary matter here. Galaxies, which in particular, I'm going to focus on the stars inside galaxies, which constitute a cold phase of the baryonic content, which may be observed in the optical wavelengths to constrain, for instance, their redshift, but also to constrain the stellar mass of galaxy clusters, or even to put constraints on the total mass of galaxy clusters. And then the second phase of the baryonic content, which is composed of gas, which is rather a hot phase at 10 to the 7 or 10 to the 8 Kelvin, which can be observed in X-rays. And from the observation in X-rays, it's possible to put constraints on the redshift of the clusters, to put constraints on the gas density, on the gas temperatures, and from these quantities to infer the gas mass of the galaxy cluster or the total mass. But the gas can also be observed in the millimeter wavelengths through what we call the Sunyaev-Zeldovich effect, which consists in an inverse content scattering of the CMB photons onto the hot gas of the galaxy clusters. And from the observation of Sunyaev-Zeldovich data, it's possible to infer the gas pressure. And also, because the Sunyaev-Zeldovich signal is independent on redshift, it's theoretically possible to detect galaxy clusters thanks to this effect up to very high redshifts. One of the reasons why we are particularly interested in galaxy clusters is because as environments of the cosmic web, they are tightly their evolution is tightly correlated to the evolution and history of the universe. And as a consequence, depending on different cosmological parameters, depending on different cosmological models, we are going to obtain different shapes of the cosmic web, and as a result, different also numbers of halos, so of clusters, different sizes also, so different masses of galaxy clusters, and also a different evolution. So sorry, okay, it's masking, but different evolution depending on the cosmic web, depending on the cosmological model. That is to say, different evolution of the properties of galaxy clusters depending on the cosmological model. As a result, the matter content of the galaxy clusters, but also the statistical properties or the evolution of their properties can be used as cosmological probes to constrain cosmological parameters. For instance, the matter density of the universe, omega m, the variance of the matter distribution, sigma 8, the expansion rate of the universe, h naught, or even the equation of state, that is to say the nature of dark energy. There are several ways to constrain cosmological parameters from galaxy clusters. There are several cosmological probes based on galaxy clusters. First, some probes based on the statistical properties of the cluster distribution. For instance, the number count, that is to say, counting the number of clusters inside bins of mass and bins of redshift. But it's also possible to use the properties of the two-point correlation function of galaxy clusters, so their position on the sky, basically, to infer cosmological constraints from the clustering. But it's also possible to infer cosmological parameters from the properties of the matter content by using, for instance, the fact that the X-ray and Swyniav-Zeldovich signals depend differently on distance, and as such on cosmological parameters. But also, we can use the shaping of the dark matter halo, in particular using mass ratios at different radii, that is to say sparsity. And one last way to infer cosmological parameters from the observation of clusters is to use the ratio of their gas mass over the total mass, which similarly is a proxy for cosmological parameters. And this particular probe is one I have used during my work. All of these different probes have been used in a collection of different works. So here, just a short example of different works that have used these probes. And all of them have handed out cosmological constraints with uncertainties on cosmological parameters of the order of roughly 10% up to 30 or 40% in the worst cases. So, yet, to constrain cosmological parameters using galaxy clusters, we need observable. We need to observe them. We need to measure the redshifts. We need to measure their masses. And as such, we need to obtain observables. However, all the observables we have at disposition comes from baryons, that is to say, from the gas and galaxies inside these clusters. Yet, as the baryons constitute less than 20% of the total matter budget, they will first they constitute only 20% of the matter budget on one side, but also baryons are a biased tracer of the complete matter distribution, as I show here in this slice of the TNG 100 simulation, where I show here the same slice of the universe in each time, and I show that the dark matter distribution and the gas distribution are not one-to-one the same. Similarly, for the stellar distribution, the distribution of stars. So this means that the baryons are a biased tracer of the matter content. But in addition, due to effects, astrophysical effects on the baryons, for instance, the presence of bulk motions of the gas, heating, gas enrichment, some shocks also, magnetic fields, or the injection of energy by active galactic nuclei, all these effects will introduce biases of astrophysical nature inside the cosmological constraints from galaxy clusters. And this will, of course, bias the cosmological constraint. And as we are in an era of precision cosmology, where the best cosmological constraints we can obtain from the cosmic microwave background are to the percent level, if we are to compare efficiently and to model accurately the evolution of the universe with galaxy clusters, we need to take well into account all these astrophysical effects which bias the cosmological constraints. As a result, galaxy clusters, they may be studied both for their cosmological properties as cosmological probes, but they may also be used as astrophysical objects of study. Sorry, but they need to be studied under both aspects to understand fully their cluster their evolution from early times up to late times. And this wide question of the cluster evolution, I've tackled it by studying at 3 particular aspects. First, looking at the interactions between astrophysical and cosmological effects, but also looking at the effects of the environment of the surrounding cosmic web on the properties of galaxy clusters. And I've also tackled the problem of the cluster mass measurements, as the cluster mass is a very important quantity for carrying out cosmological studies with galaxy clusters. This problem of the cluster mass is the one I've been studying in my first project, which focuses on the hydrostatic mass bias from the gas mass fraction of clusters, which is described also in a paper published recently. The mass of galaxy clusters is extremely important quantity to measure. And to measure the mass of a galaxy cluster, several assumptions are made always. The assumption that the matter distribution is always following spherical symmetry. Also, the assumption of a self-similar evolution, that is to say that the properties of galaxy clusters are all the same when scaled by their mass and their redshift, a bit similarly to Russian dolls, which are all the same when scaled by their size. And also the assumption of hydrostatic equilibrium, that is to say that the gravitational collapse is perfectly compensated by the pressure support of the matter. Yet, astrophysical effects from the baryons will induce departure from these conditions. And as a result, deviations from the hypothesis of hydrostatic equilibrium will introduce a mass bias, which is called the hydrostatic mass bias, which one denotes B, and which may be characterized by the ratio of the total mass estimated following the hypothesis of equilibrium over the true total mass. And I denoted grade B here, though some people may note it 1 minus B, 1 minus 1B. The problem is that different mass calibration of galaxy clusters will, of course, induce different cosmological constraints, as the mass is a base measurement for galaxy cluster cosmology. This leads to the fact here that if we try to obtain joint constraints on the variance of the matter distribution and the matter density here, depending on the level of bias we consider, depending on the value of grade B, we are going to obtain different cosmological constraints, which may lead in the end to cosmological tensions. So this is one of the reasons why we have to investigate the value and the properties of this hydrostatic mass bias. And in addition, the problem is that between predictions from simulations, direct measurements from the comparison of X-ray or SD masses and weak lensing masses, and indirect measurements. So basically, between direct and indirect measurements, there is a tension, there is a discrepancy, where simulations and direct measurements predict masses which are biased with at the order of 20%, that is to say 1 minus B or grade B of the order of 0.8, while indirect measurements from a combination of number counts and cosmic microwave background rather predict masses which are much more biased, with a level of roughly 40%, that is to say 1 minus B or grade B of the order of 0.6. And there is a tension between direct and indirect measurements. In this context, why is it interesting to use the gas fraction of clusters, that is to say the ratio of the gas mass over the total mass? Well, because the measurement of the gas fraction will, of course, depend on the estimation of the total mass. And as such, it will be sensitive to the cluster mass bias. The gas fraction, on the other hand, is also directly proportional to the universal baryon fraction, omega b over omega m, so cosmological parameters. and is also depending on the angular diameter distance, making it a good cosmological probe. The gas fraction has been used in several studies for the past years, in particular using its properties as cosmological probes. But it's only since the XCOP study in 2017 that the properties of the gas fraction to probe this mass bias was shown in a sample of 12 clusters. So here the idea is to use gas fraction measurements to probe this mass bias in a larger sample than the XCOP study, and in particular to probe the possible evolution of the mass bias, as it was shown in a collection of different studies, that it was possible for the mass bias to evolve either with mass or with redshift. In particular, it was shown that it was. So one of the ideas is to probe the evolution of the bias. But in addition, as the gas fraction is both an indicator of astrophysical effects, but also a cosmological probe, the idea is to investigate the degeneracies that exist between the mass bias on one side and cosmological parameters on the other side. To carry out this work, I used 120 clusters from the Planck early ESI sample, so selected in Suniel-Zeldovich data. And they have been observed then in X-rays by XMM Newton inside R500, that is to say, the radius inside which the mean density is 500 times the critical density of the universe by Lorenzo-Lovisan. From this X-ray data, gas density profiles and temperature profiles were obtained in the paper by Lorenzo-Lovisari. And from this gas density and temperature profiles, the gas fraction, was measured by integrating the gas density profile, and the hydrostatic mass, that is to say the total mass estimated from the hypothesis of equilibrium, was also constrained using the gas density and temperature profiles. And from this gas mass and hydrostatic mass, I computed the observed gas fraction, which is the ratio of the gas mass over the hydrostatic mass. So this leads to this distribution of gas fraction depending on redshift and depending on mass, which I compare here to the universal baryon fraction from Planck. And the idea is that I'm going to fit this distribution of the gas fraction depending on redshift and mass using a Monte Carlo Markov chain method. So the modeling which I use to carry out this study, I start from the very basic assumption that the total baryon fraction inside galaxy clusters, so the fraction of gas and fraction of stars, that is to say the sum of the gas mass and stellar mass over the total mass, is proportional to the universal baryon fraction. Yet, due to astrophysical effects, the mass bias which I discussed, but also the fact that baryons may be depleted inside galaxy clusters due to ejection of the gas out of the boundaries which are considered, for instance, due to this depletion, we need to take that into account in the observed gas fraction and observed stellar fraction. In addition, so this was the astrophysical contribution, but in addition, the gas fraction measurement will depend on distance, which is measured inside the reference cosmology. In particular, the masses, the radii, the distances, all will be measured inside the reference cosmology. So this introduces a dependence on the distance, and also an angular correction here to account for the fact that all measurements are carried out inside a reference cosmology. And this leads to the global model which I used here, where the observed gas fraction is supposed to be equal to this model where I consider also possible instrumental effects. In particular, it was shown in several works that depending on the X-ray observatory used, the mass calibration could be different. So these instrumental effects could be need to be taken into account. There will also be, of course, the astrophysical effects from the baryons. So the baryon depletion, the hydro mass bias, and of course the stellar fraction, and then contribution from cosmology. So all this part here, which depends on cosmological parameters. And and as we are here focusing in particular on the bias and its evolution, I parameterize the bias as an amplitude here, which is what we expect to be closer to 0.6 or closer to 0.8. And then a power alpha, so it's hidden here, but a power alpha encoding the mass evolution of the bias, and the power beta encoding the redshift evolution of the bias. And this work is carried out making several assumptions. First, and this is a big assumption, we assume that the depletion is constant. This baryon depletion is well tested in hydrodynamical simulations, so this hypothesis is sound. Yet, because of we already can expect a degeneracy between the depletion and the bias from the expression of the model. So here, a possible evolution of the depletion with mass or redshift could be mistaken here for an evolution of the bias. So this needs to be taken into account. In addition, I consider a prior here on the total value of the bias at a given mass and redshift, working as a pivot from which we can test the trends of the bias. A prior which is taken here from the CCCP analysis by Erbonnet et al. In 2020. I also consider that the stellar fraction is constant, and this assumption is tested in simulations, but in particular due to the fact that the stellar fraction here is negligible with respect to the gas fraction. Possible evolution of the stellar fraction will not have a strong impact on the trends of the mass bias. And finally, here, as I consider only the deviations from the hydrostatic equilibrium, I still consider that the mass distribution is spherical and that galaxy clusters have evolved self-similarly. And from these assumptions, I'm going to test 3 different scenarios to test in particular the degeneracies between astrophysical and cosmological parameters, between the bias and cosmological parameters. First, I test here a scenario where the bias is left constant. I call it CB, and because the bias is constant, alpha and beta are both set to 0 with only the amplitude B0, which is free. Then I'm going to relieve the constraints, relieve the priors, sorry, and I consider this scenario VB for varying bias, where all 3 bias parameters are left free. This time the bias may evolve with mass or redshift. And a last scenario, which I'm going to justify in a moment, which I call VB plus omega m, where similarly all the bias parameters are set free, but this time I add a prior from Planck cosmic microwave background data on the matter density here, which I'm going to discuss in a moment. And from this set of assumptions and set of 3 different scenarios, I run my MCMC and fit the distribution of gas fraction depending on mass and redshift and obtain the following triangle plot, which I'm going to walk you through. First, something which is kind of reassuring. In all cases, the amplitude B0 here is agreeing with a bias of roughly 20%, that is to say, a bias of roughly 0.8. So of course, this is completely driven by the prior set on the total value of the bias, but still, all scenarios are agreeing on that. Yet, if we focus now on the trends of the bias with mass and redshift, I show that the redshift evolution of the bias beta and the matter density omega m are degenerated. The degeneracy is such that if I impose a constant bias in the CB scenario, this pushes the matter density omega m up to very high value above 0.86, which is totally unreasonable, as most cosmological constraints point out to a matter density of roughly 0.3. As a result, this is why I test the VB plus omega m scenario by imposing a Planck prior on the matter density. I obtain here beta different from 0, that is to say, a bias which evolves with redshift. And in particular, as beta is negative, that would mean that the higher the redshift, the more biased the mass will be. So these 2 results here, the heavy degeneracy between the redshift evolution and the matter density, and the fact that for a reasonable matter density we find a redshift dependent bias, are the main results up to this point. And in particular, here it seems that the hydrostatic mass bias evolves with redshift. Yet, in several other works using number counts or using weak lensing, it had been shown that depending on the different selection inside the mass sample, the trends or the values of the bias might evolve. There was a sample dependent behavior, which we want to test here. We want to test here if we find the same sample dependence, and to test for possible sample dependence, I split my full sample here into two subsamples: a subsample of clusters at low mass and low redshift, and a subsample of clusters at high mass and high redshift. And I carry out the same study once again, but this time with slightly different assumptions. This time I put constraints on all cosmological parameters, which allows me in turn to remove the prior on the total value of the bias. And this way, all three bias parameters are left free and can evolve totally freely. And what do I get from that? Same thing. I'm going to walk through through this plot. Here, in all subsamples, and without any prior on the total bias, I always find an amplitude of the bias which is compatible with a bias of roughly 0.8. So no subsamples seem to favor a higher mass bias, so a smaller B0. Yet, similarly, the problem arises if we focus on the trends of the bias, where if I focus here on the low mass and low redshift subsample, I find alpha compatible with 0, that is to say that the bias wouldn't evolve with mass. However, beta is still in disagreement with 0, so we still will have a bias which evolves with redshift. Yet, if I consider the other end of the mass redshift plane, if I consider the high MZ subsample, this time beta is compatible with 0, that is to say that the bias wouldn't evolve with redshift, but on the contrary, alpha is incompatible with 0. And similarly, we find the scenario where the more massive a cluster is, the more biased its mass measurement will be. So what do we, yet, despite all of these problems, despite all these degeneracies and sample dependence, my constraint on the bias is always compatible with, is majoritarily compatible with other tests of the bias, other measurements of the bias, in particular with direct measurements, where I compare here my constraints of the hydrostatic mass bias to other direct measurements from weak lensing, from X-ray studies, or where I compare with simulation works and find a global agreement. However, if I compare my constraint of the bias with the preferred value from the indirect measurements here, there's still a tension with the indirect measurements, which seems to be solved only for the higher redshifts and higher masses. So we do not. So from this work, it appears that the tension existing on the value of the bias is still going on. What do we learn from that? First, that as it had been shown in the X-scope, analysis, but here with a larger sample, we still find that the gas fraction can be used as a robust test for the mass calibration of galaxy clusters. But in addition, not only the value of the bias, but also the evolution of the bias are degenerate with cosmological parameters. This points out to the fact that when testing for the mass calibration of galaxy clusters, it's necessary to also consider a possible evolution of the bias. This work and these results are globally in agreement with other direct measurements, but not only on the value. Also, some other works we try to investigate the trends of the bias with mass and redshift, find similar trends, at least qualitatively, of a bias increasing to higher redshifts or masses, with the two studies here, which find slightly different trends in particular subsamples. And this difference between the trends of these two works might be explained by possible additional astrophysical effects, where in particular here, the assumptions in particular on the depletion, of a constant depletion, may introduce the trends in mass and redshift, which are not completely due to the bias, and which are affecting only the gas fraction measurements. In addition, due to the sample dependence of the results here, it appears that astrophysics will affect clusters differently throughout their evolution, as depending on the redshift selection or the mass selection, the value of the bias and the trends of the bias will be different. This points out to the fact that we need a better understanding of the cluster evolution through time, through cosmic time, and also to understand better how they are impacted by their environment inside the cosmic web, and how this will affect the mass measurements. The study of the evolution of clusters in their environments is what I've studied in my second project, focused on the structure of multiple cluster systems, which is described in a paper recently published here, where I focused on multiple cluster systems. And why am I interested in multiple galaxy cluster systems? Well, because these particular systems are key pieces in the galaxy cluster evolution. They are considered to be systems which are still forming, and also they are considered to be some like a miniature cosmic web, where in particular, as I show here, the Shapley supercluster, which is a multiple system of 8 galaxy clusters, which similarly to the larger cosmic web shows several cluster components and bridges of matter akin to filaments between the different components. And as such, studying galaxy clusters multiple systems, allows to have a better understanding of the behavior of the global cosmic web. Also, due to the presence of gas in between the different cluster components, at the meeting regions of the different cluster components, complex physics will happen with possible mixing of the gas, possible shocks also, and this complex physics can be studied using these different multiple systems. One way to investigate the properties of these multiple cluster systems is to use galaxies, to observe galaxies. In particular, because galaxies in galaxy clusters, by their observation in optical data, allow to have an accurate measurement of the redshift, that is to say of the distance, and as a result, allow to put precise constraints on the structure of galaxy clusters. In addition, the properties of the galaxies will be modified by the environment in which they are, as galaxies have a life cycle. I show here the star formation rate to stellar mass diagram for different galaxies. In particular, galaxies, when they are young, in a way, they form along this main sequence of galaxies, where the galaxies have a high star formation, and globally these galaxies are rather blue spiral light types, and these galaxies form a lot of stars on the main sequence before migrating to a second population of galaxies here with low star formation. They are, say, quiescent with low star formation, which in majority are rather elliptical red early type galaxies. Why is that interesting? Well, because to form stars, for the star formation in galaxies, it's necessary to have a cold gas reservoir. In galaxy clusters, due to the presence of hot gas, this reservoir will be depleted in clusters due to the presence of hot gas, which will prevent the refueling of cold gas, which will also deprive the galaxies from the cold gas. And as a result, galaxies in galaxy clusters are quasi-exclusively quiescent. We say that they are quenched, at least in low redshift at redshift 0, so today in recent galaxy clusters. Now, this points to the fact that analyzing the properties of galaxies inside multiple systems may allow to study the physical effects affecting the galaxies inside these particular systems. And in particular, my work has been dedicated to study two multiple galaxy cluster systems, where for the sake of simplicity, I will just call them Planck 1 and Planck 2. Two multiple systems which have been discovered in Swinny-Zeldovich data in the Planck all-sky AZ survey, and which have been observed in follow-up XMM Newton observations. From this follow-up observations, which I show here, where the color background is the SZ signal and the black contours are the X-ray images. From this X-ray data, it was shown that the system were triple systems with three components, A, B, and C here. And as a result, dedicated observations in X-ray and in optical were decided with the objectives of understanding deeper, analyzing deeper these particular systems, where the idea was to investigate the dynamical states of the individual cluster components, to study the possible presence of filaments between the different cluster components. So this was rather for the X-ray analysis. And for the optical analysis, the idea was also to constrain properly the structure of the system, and this needed the measurement of redshifts, and also to constrain the stellar properties of the galaxies, for which star formation rates and stellar masses measurements were necessary. From the X-ray analysis carried out by Edouard Lecoq and Alexander Koloding, some hints of non-coplanarity, were found where there was some uncertainty on the redshift of the different components. And also it was shown that the different components all were in different dynamical states, with some components being rather relaxed cool core and other components being rather disturbed non-cool core. And as a result, from these different dynamical states, we already expect to see different consequences on the properties of galaxies. And the idea was to improve the knowledge of the structure from the optical data. And to study the structure, I use this optical data, so VLT-VMOS low resolution spectroscopy in the visible and near infrared regime. Basically, the full description of the data analysis is shown here, where I first went from the spectroscopic VMOS data, where from the VMOS data I obtained the raw spectra, which I reduced. So I underwent the full data reduction, where in particular I first started by calibrating the spectra in wavelength and in flux. And from this reduced spectra, I was able to measure redshifts and to determine some first galaxy type, to determine some galaxy types as a first proxy for the stellar properties of the galaxies. And so from this data, I had insight already on the structure of the systems. And then to constrain the stellar properties of the galaxies, I resorted to ancillary data, where in the case of Planck 1 here, I used the intersection between the VMOS data and ancillary data from Allways and SDSS to constrain stellar masses and star formation rates. While due to the poor quality of the data in the case of Planck 2, I resorted to adding a catalog from Basile Legacy Imaging Survey, which allowed to obtain supplementary photometric redshifts and estimation of the specific star formation rate. That is to say, the ratio of the star formation rate over the stellar mass. And from this total data analysis, I obtained the following results. So here I'm going to focus solely on Planck 1, but we may discuss on Planck 2 during the questions if you like, where I show here the distribution of galaxies depending on the redshift and so in 3D, and I show here the distribution of redshifts depending on the number of galaxies. And I give also the estimated type of the galaxies as a first proxy for star formation activity. So what appears here is that there is first two components here, components A and C, which appear well in the foreground at a redshift of roughly 0.45. And the second component B here, appears well in the background at a redshift of roughly 0.5, such that the separation estimated between components A and C and component B is of the order of more than 100 megaparsec, where for comparison, the estimated physical distance between A and C is of the order of 10-15 megaparsec. So there is so the component B is way in the background, and this hints. I mean, actually, this is proof for a clear separation between a pair in the foreground and an isolated cluster in the background here. And this is confirmed by the X-ray analysis. The X-ray redshift estimates, which find similarly a redshift of 0.45 for the pair AC and redshift 0.5 for the cluster B in the background. And I show here the position of the galaxies compared to the distribution of the gas, where similarly it appears that cluster B is the galaxies from cluster B are way in the background. So for Planck 2 here, which I'm not discussing, similarly, all three components were found at more than 100 megaparsec each. So similarly, a fully split system. Now that we have understood better the structure of the system, I looked at the stellar properties of the galaxies, and in particular, I drew this star formation rate to stellar mass diagram here, where I show that, as expected, most of the galaxies here are quiescent galaxies, so which have underwent quenching of their star formation. However, in one of the three components, in the component B here, at a redshift of 0.5, some star formation is still to be seen, is still observed. This behavior had been noted already in clusters at similar redshifts by the study by Speron-Longin in 2021, where I show here the star formation rates to stellar mass diagram of the A, B, and C components compared to clusters at redshift 0.48 and 52, where similarly the galaxy population is most of the galaxies are on the main sequence. So the behavior noted in B is not isolated. So of course, this is not something statistical. This is not something from which we can we can draw a final conclusion, but this is not an isolated case. What do we learn from that? What are the main takeaways? Well, first, with only 6 different cluster components, there were several different physical processes which are involved with one of the clusters which is still forming stars, and the X-ray analysis is showing that the dynamical states in all clusters is different. Yet, we gain no new insights on the effect of being in a multiple cluster environment. Indeed, because all of the systems here were split except for the pair AC. So we just had isolated clusters. The fact that we had non-multiple cluster systems, the fact that we only had split systems, this questions the cluster detection and characterization, in particular in AZ data, as the systems here were detected in Planck and treated in Planck as single sources. It's only thanks to the X-ray analysis that the triple nature was shown here, and then with the additional insight from optical data, it was shown that there were not triple systems, but actually split systems. So this questions the characterization of clusters, in particular as estimates from of the mass of galaxy cluster are necessary if we first considered here the SE estimate, we would have considered only 1 cluster of high mass instead of 3 clusters, 3 isolated clusters. So what do we learn from all that? I began by saying that galaxy clusters could be studied under the aspect of cosmology or as an astrophysical object of study. Indeed, on the one side, galaxy clusters constitute robust cosmological probes, yet they are also the host of complex physical processes which will bias the cosmological constraints. There is also a wide variety of objects which evolve differently throughout time, differently in the cosmic web. And we need to understand fully how these clusters evolved, how this wide variety of clusters evolved. Yet the properties of clusters, which we study to understand the evolution, are modified by astrophysical effects from the baryons. And in addition, all the cosmological observables we have come from the observations of baryons, which bias the cosmological constraints. So this led me to the idea that we need to study galaxy clusters under both aspects, cosmological and astrophysical, to understand how galaxy clusters evolved throughout time inside cosmic web. And this led me to tackle the problem by studying the interactions between astrophysical and cosmological effects, the effect of the environment, and the problem of cluster mass measurement. I showed here that the gas fraction on the one side the cosmological sensitivity of the gas fraction was affected by astrophysical effects due to the degeneracies between the trends of the mass bias and cosmological parameters. Yet the gas fraction proves to be a robust test of the mass calibration of galaxy clusters. In addition, the study of the gas fraction allows to study the effect of the mass calibration and the effect of the mass calibration on cosmological constraints by studying the degeneracies between the two effects. Yet, the exact evolution of the bias is still unclear, as the study from gas fraction was not sufficient to solve the tension between indirect and direct measurements of the mass bias. In addition, the study of multiple cluster systems showed that we needed to have a particular attention to cluster detection and characterization, as without a full multi-wavelength study of Planck 1 and Planck 2, then the systems will not have been considered as a 3-split system, but rather as one Sunyazev-Dovich source, or at least as three coplanar X-ray sources. And we did not gain particular insights on the effect of being in a multiple cluster environment, and we need for better data to investigate the effect of multiple cluster environments. And what do we go from there? What's next? One path to follow would be possibly to obtain a more thorough understanding of cluster evolution, in particular by studying a larger sample, a larger population of multiple galaxy clusters. And this will be allowed, for instance, by large optical surveys like Euclid, which started to take data and which will allow to have a wide variety of multiple cluster systems studied in optical wavelengths. So this might be one path to take. The other path that we may take will be to investigate the physics which fuel the mass bias, because of course here the only assumption I consider was that of a deviation from hydrostatic equilibrium. However, deviation from self-similarity may also introduce a mass bias. The presence of non-thermal effects may also produce this mass bias. So using parametric profiles for the mass measurements similarly may introduce bias. So this may be a path, and this is a path actually which is followed by several works here at IAS, but also throughout the community. And one final path here will be to try and break the degeneracies between astrophysical and cosmological effects. And this last path here is one I am currently following with the project I am currently carrying out, where the idea is to combine the gas fraction with galaxy cluster number counts to benefit both from the astrophysical sensitivity of the gas fraction and the cosmological sensitivity of number counts. And I have started here obtaining some results, which I will be happy to discuss during the questions. Thank you very much.
Thank you, Raphaël, for this dynamic presentation. You're very a large amount of results.
Yes.
Maybe we can start with
people are. We can wait for people to flee the questions.
Just to refresh. Take a long breath.
Yes. Respire.
Yeah.
We are going to start the session of questions, and maybe Veronica from Trieste is ready to begin.
Yes, thank you, Raphaël, for the nice presentation of your thesis work. And well, out of personal expertise and due to the expertise of the other members of this committee, maybe I will mostly focus on the second part of the work that you have presented it in the presentation. on the multiple systems and their galaxy properties.
Yes.
And perhaps I would start with somewhat technical, but not too much also technical, let's say, question on the samples of galaxies that you have used and on the impact this may have on the results of your work.
Yes.
In particular, as you have said in your presentation, you have used, especially for Planck 1, you have used the intersection of the BMOS data with ancillary data from SDSS and All-Wise. And so I was wondering how this intersection depends on the quality of the different data, in particular on the depth, of course, of the relative depth of the different data, on the spatial resolution, especially if you match by positions of sources, as I understand from your thesis, and also in particular, in the very first place, on the target selection of the BMOS sample, which, of course, I assume has significant relevance in the results that you derive. Do you have comments on this?
So I guess I'm going to start by the end of your question and the selection of the VMOL sample at first. Then I'm going to switch to the ancillary data. But your question is also a comment which I've read in your report, and is very true actually, because so basically the selection of the galaxy sample was so I did not find many informations in the observation proposal, because one of the main goals of the optical part of the project of the data of the observation proposal was to constrain really the structure of the systems. And the first idea of the optical proposal was really just to measure redshifts. And I did not find in the observation proposal much more information on the particular type of galaxies which were to be selected. So no clear evidence of rather focusing on the red sequence, or on the contrary, trying to be as random as possible in the selection. So this is of course an effect which will impact the stellar properties section. So this is one thing. The main goal of the optical follow-up was to constrain the structure, not pretty much to go further. So that's one thing. And the second part of your question about ancillary data, I'm not sure I fully remember what you asked.
Well, I was wondering in particular if you match your BMOS sample with All-Wise, for instance, or on the other hand, on SDSS, you will have different issues related to the relative depth of the different data sets, and also in case of WISE or of spatial resolution. So I was wondering if you have a comment on how much this can affect the final sample. I mean, what is the final sample selection of your galaxy sample or candidate member sample that then you use for the scientific analysis?
So here the match between, sorry, the matching between the always rather SDSS data and VMOS data was a simple positional matching. That's on one side. And regarding the spatial resolution or else, so I'm not fully sure if this will answer your question, but the coordinates for each of the galaxies here were taken to the VMOS coordinates. So in the end, if we look at the spatial distribution of the ancillary data, we are just looking at the VMOS position, VMOS galaxies. It just basically we have VMOS data plus for some additional SDSS and always flux measurements. I don't know if this answers your questions.
So, for instance, if you do not have a match for a VMOS galaxy, what do? You use upper limits, or you just throw it out?
So, okay. So basically, for the structure analysis, where I really look at the spatial distribution of the galaxies, I only use the VMOS data, and I use the ancillary data from always and SDSS just for the study of the stellar properties. And here I did not I did not look too much at the spatial distribution. So I just so basically it's two different works, and the always data just come into play for the study for the SFRM star diagram. Sorry if I come back.
Yeah.
So here I show with my mouse this plot and the following one are basically the only two where the ancillary data from always and SDSS are used.
And in these cases, then you use upper limits where you do not have a counterpart, let's say in your catalog, for instance.
Here it's only I only show the galaxies for which I have flux measurements in the ancillary.
Yeah, I understood. So going from this technical point to the related science point, do you think this has an impact on the results that you retrieve? For instance, normally, if you look for maximizing your success rate for a spectroscopic follow-up, in particular, if you just need redshifts and you do not plan to study galaxy population properties, of course, you try to target the galaxies that most likely are cluster members, which are typically quiescent galaxies on the red sequence. So, of course, this already from the start biases the sample. And unless this is accounted for, of course, this impacts on the result of perceived results on galaxy population properties in these systems. Do you think this as an effect? Have you tried to compare your results based on the VMOS sample, for instance, with results from photometrically selected parent sample from the DAISY catalog, for instance, in particular for Planck 2?
So, so yes, going from the beginning of your questions, yes, of course, this will have an effect. This will bias the complete SFRM star diagram. And also, if I'm trying to think on how to phrase it properly, I think that this more or less drives us to have some qualitative results rather than purely quantitative. As for instance here, to estimate the complete star formation rate of the cluster in one sense, I can only give lower limits from what I have here. So yes, we are very much impacted by the fact that the way the sample was designed was just to constrain the structure of the systems.
The photometrically selected samples just from photodesics from DAISY would help you in trying to recover the truth, let's say, or something closer to.
Yes, that's something I try to do for Planck 2. So I'm telling you first before showing you the plots. It's not very pretty, but I try to compare in DAISY. Sorry. So here in DAISY, what you see. Sorry, it's really not pretty. But what you see is the galaxies from the DAISY photometric sample, where all the gray dots. Sorry, I'm going to show you with my mouse. All the gray dots are field galaxies taken in the field of Planck 2, while the crosses or stars, etc., are the identified cluster numbers. And so basically, I mean, the only thing we more or less get from that is that the majority of the population is rather quenched. But I did not compare further with the global population of DAISY, and this is something I could try to do.
I see. What about the estimates of stellar masses and star formation rates that you are plotting, for instance, here or also in the other case? Do you think what is the expected reliability of these estimates, in particular for star formation rates?
Yes, so here, it's true that I don't show the error bars. One of the reasons why is after discussion with Denis Burgarella, one of the people behind the code SIGAL, we were not fully sure of the reliability of the error bars. So here, I'm trying to following the different tests that were made, and also by looking directly at the fits and at the data, I would say that they are rather reliable. I mean, they maybe each galaxies will move a bit inside the main cloud, but not go to very low or high values of star formation rate and stellar masses.
So let's say you do not trust maybe accurately the actual estimate, but you believe this is fine to separate quiescent and star forming systems with no degeneracy between the two.
Yes, that would be
okay.
Discriminating between quiescent and star forming. This I trust. Yes.
Okay, but maybe one different point that was partly raised in your presentation, but was appearing more strongly, perhaps of course, in the extended version that you have in your thesis. What do you think was the actual relevance of the VMOS observations, in particular for Planck 2, given the complications that one could expect even from the start? Because, as I said, the D4000 was not in the spectral range, and there is this OH line contaminating the spectra right at the wrong position in the spectral range. So do you think these data were relevant in the end, or when you say that you had to add the DAISY data rather than intersect with the ancillary data as you did with Planck 1, you mean that these observations were not particularly relevant for the analysis of this structure?
So in the case of Planck 1, yes, they are fully relevant because they allow to properly constrain the structure. In the case of Planck 2, I agree that it's a bit more complicated, but still the VMOS optical data allowed to put precise constraints on the redshift of the components, because what we had from DAISY ancillary data was photometric redshifts from the galaxies and a photometric redshift for each of the three groups, and the addition, the presence basically of the VMOS data allowed to put precise constraint on the redshifts of at least component A and B. For component C, it was a bit more complicated.
Mm-hmm. Yeah.
I'm trying to find the slide somewhere in my backup. Yeah. So basically, from the VMOS data, it was possible to constrain properly and robustly the redshifts of A and B. For C, indeed, the VMOS data did not have much relevance.
I see. And concerning instead the structure rather than galaxy properties of these systems, you conclude in both cases that besides the one cluster pair in Planck 1, these are incompatible with these components are incompatible with belonging to superclusters.
Yes.
What is I thought if you could comment more specifically on the argument, I assume a statistical argument on the distribution of protocluster sizes and the separations between protocluster components.
So here I'm going to show you a plot which Edouard Lecoq has done for Planck 1, and then we are going to discuss on it. For Planck 1 here, I show the comparison. So the points here are different identified multiple galaxy clusters in SDSS, and in particular their stellar mass with respect to their size, to their diameter. And for Planck 1 here, Edouard Lecoq shows that if we consider only components A and C, then the system is fully in agreement with the rest of the population, of the supercluster population, for this radius with this given mass. Yet, if we consider the additional component B, then this time Planck 1 is rather in disagreement with the global population of multiple galaxies, of multiple systems. So this points to the fact that Planck 1 is a pair and an isolated cluster in the background. So this is for Planck 1. And for Planck 2, if we consider a separation of 110 megaparsec between each component, all the while keeping in mind that the stellar masses of each cluster is lower than that of Planck 1, in particular for B and C, then we will be in this regime here, even more incompatible with the system being gravitationally bound. So here I'm showing it to you with my mouse. I did not properly do the plots, but still this is a hint at the fact that indeed these three systems are just three systems aligned along the line of sight.
What is the stellar mass on the y-axis? Is the total stellar mass of all the components added together?
Yes.
And it is from your samples or from independent estimates?
From SDSS, the DR7. So from the paper of Liva Maggi.
No. I mean, in your case of Planck 1, I mean.
For Planck 1, yes, it's estimated by it was estimated in the study of Edouard Lecoq.
Okay.
So, yes.
Okay. I guess I have to shut up. Maybe if I can ask just one very last thing, very quick reply, or perhaps we can postpone it to the other questions on that part. I just was wondering to what extent, for the other part of the work, I was wondering to what extent you may expect to constrain the combination of mass and redshift dependence of the bias if your sample is limited in the distribution in the mass and redshift plane in the way you showed in one of your slides. Maybe line 27, maybe I noted it down, the number of the slide.
How significant the trends are?
Well, no, if you to what extent you can constrain simultaneously both, given that, well, exactly, as you see from, I mean, given that there is a patchy coverage, let's say, of the mass and redshift plane, where you basically have less dynamic range in mass at high redshift and vice versa. So you probe different regimes in mass at low and high redshift. That's what I mean. So,
of course, because of the low redshift and mass range, the constraining power is lower, and this can be easily seen here in the posterior distributions, where for smaller subsample the posterior distributions are way wider, and so one of the possibilities that we investigated was that in so small selections, because of the because sorry, I'm trying to phrase properly. The mass distribution of the sample is redshift dependent. I mean, we detect more massive clusters at high redshifts, and this effect might have impacted our trends. So we tested for this possibility by cutting the sample in by performing selections where the mass distribution doesn't evolve with redshift, and we find the same trends. So I'm not sure this fully answers your question, but basically, yes, we see that we have less constraining power due to the size of the posteriors, but we do not introduce new biases just because of the ranges, the selected ranges.
Okay, thanks a lot for your questions. I stop here. Thanks a lot.
Thank you, Veronica. Stéphane Wettery from Bologne. Are you ready to ask questions?
Yeah. So I would like to start from Planck 1 and Planck 2. You mentioned the fact that they were detected as a single source.
Yes.
So can you speculate a bit, or can you plan how you would correct the total flux from Planck, given the knowledge that you have of the substructures? And can you work out some algorithm or recipe to recommend Planck people to correct the flux according to what you know about the image structure?
Oh, tough questions. So here, so there are two effects which will need to be taken into account. I'm not fully sure on how to answer this question. But basically, here, if we consider for A and B, for instance, the fact that their signal is going to be added in a way because the SE signal is integrated along the line of sight. I think for that we cannot work on SE alone. We need the input from X-rays, I'd say. I'm not fully sure on how to answer the question. But
for instance, if you have
actually, so here, at least from X-rays, you can constrain the YX, so estimate more or less the expected SE signal. So you could estimate the expected SE signal for each three source, and then try to take into account the fact that it's blended because of the wide beam, but then on how to implement it fully, I'm not fully positive. I could. Yeah, I'd say the starting point is first estimate the expected SE signals for each of the three components, then see how it because also there's the geometric side, because here we know that there will be some overlap of the SE signal, while between A and C it's not so sure. So yeah.
So you can think about a model of the halos and universal pressure profile.
Yeah.
You probably you mentioned already, but how many of these multiple systems are expected in cosmological center of Planck, for instance?
So not many. That's a good thing. So in the Planck studies, in particular the Planck 2015, it was estimated that there was roughly 10% chance to find chance cluster and an expected cluster in the 5 minutes beam. But from what I understood, it's rather finding low mass systems, so rather groups rather than actual clusters. And here in the full sample, so if I remember correctly, so in the full Planck, the full PSC2 sample, there were more than 1,000 clusters. There were 5 or 6 which were identified as projection effects. and a few more which were identified as actual multiple systems, so mostly double systems. But yeah, of the order of maybe 10 or 20 on the full 1,000. So for cosmology and for number counts, this should not be that big of a problem if we have 20 clusters which are a bit more, I mean, which are taken more massive than they are. I would say. So the order of 10, 20.
Okay. Coming to your presentation, that indeed was very nice and very comprehensive and very detailed. I appreciate a lot. At some point you state that all observable come from baryons. I think I also pointed out in the report. What about lensing? So lensing is something that is a signal, very neat signal.
Yes.
That come not only from baryons. At least the interpretation, of course, the signal is distorted galaxies.
Yes.
But how you interpret this is playing a role of dark matter.
Of course.
So there was a rationale behind your statement that all observable come from baryons?
So it was more said in the idea that what we observe in the end, except if I'm not going to go to multi-messenger astronomy yet, but if we focus on multi-wavelength astronomy at first, we look at light. And the light is emitted, absorbed, scattered by baryons, and even in the case of dark matter, which we can prove via its gravitational lensing, it's always light which has been emitted at some point by baryons. So this is more in this philosophy that I was saying, because I mean, of course, I'm not denegating the positive impact of weak lensing to probe the dark matter.
At some point in your conclusion, you state that the gas fraction is a robust test for mass. I'm not sure to agree on that anyway, but and then there are exact amount evolution of mass biases still unclear.
Yes.
Are not these two sentences a bit in contradiction? Or either you know or you don't. So,
so here,
I don't want to push you in difficult, but just understand what you're talking about.
Here, at least it was at least meant in the way that it could bring competitive estimations of the level of bias and competitive estimates of the mass calibration, and which is here still unclear because of the discrepancy between direct and indirect measurements. But still, with the gas fraction, we are obtaining measurements which are fully compatible with the other direct measurements. So,
but after your exercise, you don't feel that a lot of assumptions are required that way. So a lot of astrophysical.
Yes.
We're working on gas fraction since the last 20 years, and we understand that you need to know a lot of the physics, and you have to assume a lot of the physics that are inside. But what is, after all this exercise, all this test, what is your frank opinion about how you can deal and how robustly you can constrain this astrophysical assumption in getting then some valid and robust cosmological tools?
So my point of view will be probably to go in the direction where I'm going for now, to combine different probes. So of course, my last project is still not fully advanced, so I don't know yet how many results we can get from that. But my guess would be that to fully benefit from the astrophysical sensitivity of the gas fraction, we need to combine it with other probes. Here, combining with number counts, the first results show that it allows to obtain constraints on the bias without putting any prior, and also cosmological constraints. So this would be a good trade-off And then, of course, we still need to make assumptions on the other physical problems like self-similarity, the presence of non-thermal pressure, the problem of the baryon depletion. And this, I'd say that the gas fraction can still be a relevant test, a relevant probe to look at, but needs to be studied in combination with other probes to fully understand all the big picture, I'd say.
Can I make last question? Okay. Can you just tell me or illustrate what are the physical sources of the B parameter? You treat B as a number.
Yeah.
But there are a lot of physics.
Yes. Yeah.
Can you explain me what are the main source of the origin of B different from 1?
Well, so there may be, I mean, there are several effects. There may be feedback from active galactic nuclei, some energy injection, which will perturb the gas, which will create possible shocks, possible perturbation of the gas content. In turn, the presence of perturbations of the gas content, because we generally assume parametric profiles to fit the gas density, the gas temperature, which in turn allows us to estimate the total mass. Then, because the profiles are not properly fitting the actual density profile or temperature profiles, this will of course introduce a mass bias. Also, because the mass measurements, I show it in the theoretical modeling, but the assumption behind the constraint of hydrostatic mass is that all here, basically, all of these equations are accounting for thermal pressure support, and just thermal pressure support. So also the impact of pressure support, which is not non-thermal, so magnetic fields or else, will also introduce a mass bias because they are not accounted for here in this measurement. So yeah, perturbations of the gas, non-thermal pressure, and these are only just a few of the effects which can trigger a mass bias.
Okay. Thank you.
Joran Weller from Munich, are you ready to ask your questions?
Yes, I am. Thank you. So first of all, Raphaël, congratulations for some really nice work you have done in your thesis. Also, congratulations to your supervisors, how they guided you in that direction. So let's see. So the first thing which wasn't clear to me is, if I understood correctly, you haven't used any strong or weak lensing data in your analysis. So as you know, in one of your first plots, you showed sort of, you showed this restriction to, I don't know, weighing the giants, and so I was a bit surprised that you didn't try this. Can you tell me something? Maybe the data is not public and I don't know, or why? I could have imagined you could augment your analysis, at least for a handful of clusters, by using this data.
So, is the question why I didn't use weak lensing data to?
Yes.
Okay. Well, for some of the clusters in this sample, weak lensing data were available. Yet one of the reasons why I did not use it was because it had been done by Lorenzo Lovisari, where the estimation of the bias from the comparison of X-ray and weak lensing mass was done in this sample to find similar value of the bias. So one of the reasons was it had been done already.
Okay, so but this is not in your table here somewhere, or is this in your table, what you just show on the screen?
True, it's not in this table.
Okay. Oh. All right. So let me, I wrote lots of questions. Yes, so another question I had, and look, I mean, I should have, all the questions I ask you, you know, you might ask back to me, why didn't you think about this? So is it possible, you know, so actually in your table, you know, so if I understand, you know, your X-ray gas, F-gas constraints come from X-ray observations, while, you know, the Planck observations come from SZ observations, that there's an additional bias between X-ray and SZ is something, well, I've never considered, but it just came to my mind when you gave your talk, and I was wondering what your thoughts on that are.
It is a possibility because some works have compared X-ray and SZ masses to not always find a ratio between the two of 1. So this may be an effect. I don't know, but the effect of the possible bias introduced by using X-ray rather than SZ is way smaller than the one expected from deviations to the hydrostatic equilibrium. It's from the top of my head, I think the ratio between the two, I mean, there's maybe 5% disagreement, a bit less than that, I'm not fully sure, between while the hydrostatic mass bias is closer to 20%. I'm not, yeah, I think it's maybe
It's probably mass dependent.
Yes.
Yes. Okay, maybe, so, God, this slide, I actually have, well, 2 questions. So maybe first related to your answer right now is, you know, I think you use a mass definition of M500, or at least I saw that somewhere. And I guess somewhere deep in this analysis, or in this type of analysis, is also assumption of the profile, of the density profile of galaxy clusters. And the question would be, I mean, you're alluding to it a bit, you know, with spherical assumption and so on, but that could also play a role, or the uncertainty on that.
Yes. Yes. Do you mean in this particular example, or?
Well, in your analysis, you know, or did you play around with other mass definitions? I don't know, M200, you go further out and you get maybe less or more scatter or things like that.
I didn't try with other radii. At the very first, sorry, in the very first beginning of the project, I looked at M2500 masses, but just, I mean, not for long, so I didn't go as far as I did there. And one of your other concerns were if I had investigated other deviations from self-similarity or sphericity. Am I right?
Mm-hmm.
Well, I have not studied the deviations from sphericity, but I have studied the possible effects of deviations from self-similarity, in particular following the study of Lorenzo Lovisari, which computed the masses for this work. And it appears that assuming deviation from self-similarity would introduce both the mass and redshift dependence of the gas fraction, which would then be degenerated with the bias. I started carrying out some tests to study to what extent properly deviations from self-similarity would introduce mass and redshift evolution of the gas fraction, which would not be due to the hydromass bias, but I haven't. So basically here, the idea is that it's the mass and redshift evolution of the gas fraction that we see is most probably a joint effect of an evolution of the bias and a deviation from self-similarity, but we did not succeed in breaking the degeneracy between the two effects.
Okay. And then another question the graph you're showing here. So in the Planck, first of all, in the Planck analysis, was there also parameters like alpha and beta, or was it just a constant hydrostatic bias?
It was considered constant.
So, in your plot here, it's not really comparing like with like, or if you don't allow for variation. So, the gray region, if it's constant, it might be biased towards the high mass, high redshift clusters,
Yes, I agree. Actually, most of the comparisons are, I'm mostly comparing with works which consider a constant bias, which is also the case for CMB. And I'd say it was partly a displaying choice.
I think the least what could happen, the gray region might be much larger. If you open up this parameter space, it could be.
Maybe, and I think depending on also depending on the cosmological model we consider, this band here is moved up to either lower or higher values. So. Maybe a bit more. Here, I just took the baseline result from the Planck study. Yeah, and
or maybe I can turn this around. But I think you showed this, or you did some analysis where you with your data where you only fitted for B0, or
yes,
maybe you can show this again. So where was this? This is the red, or the red region. Yes. Well, that looks very similar in B0, to be honest. Yeah, so it doesn't shift around.
Yeah, it's mainly because of the prior set on the total value. If I consider here the sample dependence test, I don't put any prior on the bias, and similarly the amplitude is always agreeing. At the pivot value, it's always agreeing with.
Okay. Okay, and then sort of finally, I want to ask you, and maybe this goes along the lines what Stefano asked. So you find, at least for the low redshift, low mass clusters, that beta is smaller than 0, and I was wondering if you have a physical interpretation to this.
What beta smaller than 0 means is that basically the higher you go in redshift, the higher the mass will be biased, and this, so with the hands in a way, this might be explained by the fact that at higher redshifts we are, I'd say, expecting to see clusters which are younger, still not fully relaxed, and which may be prone to more astrophysical effects, more disturbance, and as a result, it's really more biased performance. But this is just but yeah, I would say because of the clusters which are still forming, evolving at these redshifts.
Okay. Thank you very much.
Thank you. Dominique Wicker from Genève. If you're ready to ask some questions.
Yes, thank you very much. So thanks on the presentation and the thesis. It was very well written, so I enjoyed it. I enjoyed reading it. One question, something on the modeling of the mass bias that surprised me is that you don't actually put priors on omega baryon for this particular analysis,
for
right?
this particular, no.
While, and in fact, when you look at the formula for the how gas fraction is related to mass bias, then it depends clearly on omega. Well,
yes,
on the
yes.
cosmic baryon fraction.
Yes.
And in the end, it seems to me when I look at your posterior plots that indeed your bias values are driven mostly by the prior that you put, which comes from weak lensing, rather than from the actual F-gas values. And then the actual F-gas values is changing the value of omega B that you are fitting. Can you comment on that?
So here, you mean?
Yes. So here, the bias stays the same, and then if I look at omega B over omega M, then this is what changes from one case to another.
So basically here, so you're right that the gas fraction and the baryonic fraction are are totally proportional. My point of view on really the modeling side is that following the priors, I'm going back to the equation. So basically, this is there is a prior on that, and we expect it to be close to 1. Similarly, there's a prior there, and there's on the first part of the analysis, not the second one, but on the first part of the analysis, there is a prior here. Here, the angular correction, because we are close to the reference cosmology, is always close to 1. Similarly, here, this has a prior. So basically, because the gas fraction is of the order of 0.14, 13, what is left to fully vary, other than the evolution of the gas fraction, is just the baryonic fraction. So this naturally goes to 0.14, 15. I don't know if that's your question, but
yes, but my question is more why did you make this choice? Like, it seems to me that omega B is a very well measured quantity, while the mass bias is not. So I would have made the reverse choice, which is to put a prior on omega B and rather try to infer the mass bias.
Yeah, so this was partly due to the philosophy of the test and of the modeling choice, where in the first analysis, where I really just look at the degeneracies between bias evolution and cosmological parameters, I want to have at least the omega matter free and at least omega matter free. And the thing is, I modeled the baryon fraction as one full parameter rather than the ratio of omega B over omega M. So that's why here cosmological parameters are left free, and because of the degeneracies between the astrophysical and cosmological terms, I put this prior here. I don't know if I'm being fully clear, but on the second part of the analysis, because I really want to study both the value and the evolution of the bias, then I need to put priors on all cosmological parameters to leave the bias completely free, and that's what I do here.
Okay, so on this plot, you have a prior on omega B
over omega M. I have a prior on the baryonic fraction.
Okay, so it means that this plot probably does not depend on what value you assume for the prior on B0, like what you did with the CCCP.
Yes, so, exactly. Basically, here it's fixed cosmology. We just look at astrophysics.
Yes, so that's what I want.
Yes.
Good. Next question is about the depletion factor. You said that you assume a constant depletion factor.
Yes.
And since you are familiar with my list of publication, you know I may not necessarily agree with that particular choice.
Yes.
So I wonder what would be the result of a mass-dependent depletion factor on some of your results here.
because the two effects are fully degenerated, what we would get, at least on the mass, it would not affect too much the redshift evolution of the bias. That's my guess, because there's a slight degeneracy between the two because of the redshift dependent mass distribution, but not that big. So that would just affect the mass evolution of the bias and the most probable outcome, because the two are fully degenerated, and that's actually something I tested in the very beginning. My guess would be that we would have a degeneracy line between the two. Without being able to fully disentangle the two yet.
But like the trends that you see with alpha and beta and with the difference between the two subsamples, can they be reconciled if you have a mass dependent depletion factor? If
we know precisely what is the mass evolution of the depletion factor, then maybe. But if we leave both the depletion, the mass evolution of the depletion, and the bias, the mass evolution of the bias free together, then we will just have different degeneracy lines, because basically what we are measuring here in the end is just the mass and redshift evolution of the gas fraction. It's just the modeling hypotheses which are motivated, which allow us to say that it's due to the bias, but I agree that one of the limitations is some of the assumptions. So here, to come back to the assumption of constant depletion, I agree that depending on the mass range, especially at low mass, the depletion evolves with mass. Yet, in the mass range I consider, this evolution of the depletion is thought to be minimal, if not non-existent, because it's especially strong lower than 2 to 3 to the 14 solar masses, I guess, and we are above that range here. So that's the motivation behind the depletion.
Thank you. And another point that I noted was the fact that if you measure gas fraction, you need to assume a radius.
Yes.
And this radius, in that case, you take it from heliostatic equilibrium.
Yes.
But if this radius is wrong,
yes,
then the gas mass is wrong as well. And this affects the gas fraction.
Yes.
So the gas fraction is depends. It changes less when you change the mass. Then it's not a linear trend. But so like, are you taking this effect into account somewhere in your modeling?
Unfortunately not, but I fully agree. So here, one of the tests one of the minimal tests to ensure that we were not too affected by the radius measurements was to compare the R500 from XMM Newton to the R500 measured by Chandra of the same sample, which were available. And the R500 in both cases are agreeing. So at least that's a good point in the direction of not being biased by this possible effect. But I agree that this might be an actual problem. Yes.
Okay. One last question. Okay. Yeah. Okay. So I had one point about your last chapter of the thesis, where it presents this new cosmological modeling. So I found it was very interesting when you had this figure where you showed the impact of using different priors on the depletion factor. Yes, this figure. So let's say from my biased view, if I look at this, can I conclude that your result here shows that if the mass bias is really so low, then our depletion factor has to be way off?
I think this is more a, I mean, if I'm trying to think if it's not just modeling, but so if we consider that the constraint on the bias from the gas fraction here is indeed this low,
then it means that the depletion factor has to be much lower than what is currently assumed. Is that correct?
This, I mean, that's where it would, I mean, that's the direction this modeling pushes to. I mean, if we fully trust the modeling which we assumed for the gas fraction, then yes. But then my opinion on that would be that this may also be a hint for physical effects not first considered in the constraining of the gas fraction, more than really just the depletion, which is way off, because it's rather well constrained actually in simulations. That's my 2 cents in the question, I'd say.
Okay, yeah. Yes, I'm done as well.
I'm going to try to ask a question. Even your work is absolutely not in my field of research. On your page 24, you made the assumption of self-similarity.
Yes.
Can you comment a little bit on this and about consequences? Or
yeah. So the idea of self-similarity is really that all clusters are more or less like Russian dolls, so all the same except their size or mass. Here, this has, I mean, you are wondering if this assumption has an effect on the results. Basically, yes. So basically, we tested the possible effect of a deviation from self-similarity, and if we do not consider self-similarity, this introduces an additional mass and redshift dependence of the gas fraction, which is degenerated with that of the bias or that of the depletion, depending on the mass range. But this will induce an additional mass and redshift dependence, for which we tested from the work by Lorenzo Lovisari, which investigated the deviations from self-similarity inside this particular sample. And what we got from these results was that the two effects were degenerated, and we could not fully disentangle between mass and redshift evolution of the gas fraction, which was due to the bias, and mass and redshift evolution of the gas fraction, which was due to the self-similarity. So it's most probably a combined effect of the two. And this needs to be well taken into account. Yet one of the drawbacks, if I may say, inconvenience, is that the test of self-similarity from the work by Lorenzo Lovisari was carried out on gas masses and hydrostatic masses. So self-similarity was tested on hydrostatic masses rather than true total masses. So it's not fully clear if the deviation from self-similarity is actually due to astrophysical effects, including the bias, or if it's a true deviation from self-similarity in the gas mass to true total mass relation. Hence, why we cannot fully break the degeneracy between the two effects. Okay.
Les membres de l'équipe de direction de thèse souhaitent-ils faire un commentaire?
Je ne vais pas poser des questions.
Je ne t'ai pas posé la question, tu as une question, regarde.
J'en ai encore plein. C'est jamais complètement fini un travail. On va les garder pour plus tard. Non, je voulais juste. Sorry. Just make some comments on the 3 years of PhD that we spent together. First, I would like to remind that you started in some kind of situation called COVID. It didn't make it easy to start a PhD and start learning stuff when you make a lot of Zoom. Everything goes on remote meetings, etc., etc. So it's not, we didn't count the Zoom. Could have been nice. It's also frustrating from your part, I guess, that the first year there was no live conference. Everything was again on Zoom. And it's also changed the way you interact with people, you learn, you discuss, and so. Okay, the conditions were what they were. You managed to do your PhD, to finish it, and to publish everything. So I can be happy about that, given the difficult stuff. And we are happy about that. I mean, I will let the other one say what they want. Also reminding that you've been teaching during these 3 years, every year, sometimes at night, because you were doing the Drupal things. It finishes, I don't know when. And it's hard to start in the morning to work again. So, and you also did a lot of public presentations, outreach as well. So it's really nice that you do that, and I know that you enjoyed it a lot, teaching especially. But obviously, on 3 years of PhD, it takes time. So, you managed to do everything as well. I'm happy that you brought the expertise on the Baryon fraction stuff, because we worked a bit and a lot on number counts and using clusters from cosmology on this way. We never used ourselves the Baryon fractions, so it was new to the team. And the work you did at the end of combining the two is an example of where we were heading to by putting all the expertise good on that. So that's good that you started that as well. But the last thing I would like to say is that I'm quite happy that you are today in one piece. You managed to arrive there it has not been necessarily the case along your PhD. We've seen some casts now and then.
You need a dangerous life.
Yeah.
Yes.
But you still continue, even with some casts. I've seen you snorkeling in Réunion Island. So it was nice to see you fight for everything, even with whatever you had broken. So I just finished there to say that it was a pleasure to work with you during these 3 years. And now, in a few hours, you will be free to watch the rugby team and Rugby World Cup as you please.
Laura or Nabila?
Okay, I go. So it's me. So I'd like to congratulate you sincerely for finishing your PhD, and to congratulate you for the work that we have done together and that you have finished. And it's essentially the work which is related to the supercluster, or the so-called X superclusters that Planck discovered. Again, saying that it was something which we started, in fact, 1 week after you started working, because 1 week after COVID started, so we had to change the topic of your research. It was supposed to be a short project, and it is a project that, in fact, you have entered without knowing the background and without knowing the preparation for it. So the data was dating back 10 years ago. The planning of the observation and the planning of the sources and the planning of everything was done without you knowing anything about it. And you managed to do an extraordinary work in terms of data analysis and in terms of pushing this work until the end. It was complicated because when we started it, we were planning to have collaborations inside the team with people knowledgeable of galaxy evolution and galaxies, which eventually was not the case. It was complicated because we were supposed to collaborate with people from outside the institute on a tool that was supposedly providing us with everything, which was not the case. And eventually, it's only after like 2 years and more from the beginning of the work that you managed to put all the story about those multiple systems to the end, to a publication, which I think will be very interesting to push forward in the future for other aspects. So I really think that you made a huge work. It was complicated for you to work on this type of studies and data in an environment which was not at all prepared to. Nobody was a specialist of optical spectroscopy, VMOS, not to mention SIGAL and other things. And you did a pretty fantastic work with respect to the conditions. I'm also happy that you're so nicely fit. What I don't understand is how come, so this will be my only question, that you stopped breaking things on your body when you stopped working with me? So is there or is there a causation? I don't know. And I hope you'll stop watching and playing rugby in the future.
Dear Nabila, the reason why I stopped breaking things is because you forced me to stop breaking things. And I let you know that once this is over, I'll probably get back to doing it. So we'll see.
Yeah, so I arrived a bit later in this, let's say, adventure of the PhD thesis, and you are officially my first student. So I have to say that I hope that I've learned as much as you from this process, and I hope that I didn't screw up much during the process, but it has been very, very interesting to work on the F-gas, on the gas fraction project, and to put together the expertise that we had and what you were learning during the process, and so to learn lots of things also on my side at least. And so I hope that you will bring all these new inputs with you wherever you will go in the future. And
est-ce que quelqu'un dans la salle titulaire d'un doctorat se sent poser une question? Alors, le jury va se retirer pour délibérer.
Can you hear me well?
Yes, yes.
Okay.
Donc, je vais vous lire le rapport que le jury vient de rédiger en anglais. Excusez ma prononciation. In its thesis entitled Baryons in Galaxy Clusters, Astrophysical Effects and Cosmological Constraints, Mr. Raphaël Wicker presented his work on his modeling of gas mass fraction for cosmological purposes from Planck and XMM Newton measurements, and the analysis of and modeling of two multiple galaxy cluster systems. scientifically valuable work discussing in a clear way interesting and original results. The topics covered are well inserted into the framework of open issues of our understanding of galaxy clusters and the formations of large-scale structures, and provided a solid contribution to the field. This is a very significant and novel work, providing a method of key importance for upcoming cosmological surveys, using a large amount of data analyzed. Mr. Raphaël Wicker demonstrated a high level of independence and provided a very significant work of data analysis, in particular in the optical study of the multiple clusters. In this dynamic and detailed presentation, he showed his ability to discuss and present results from two different topics in a coherent physical picture. He managed to answer clearly the questions asked by the jury, demonstrating his good understanding of the subject. The jury is pleased to see that the recommendations of the referees were taken into account in the presentation. Mr. Raphaël Wicker is the first author of two papers published in A&A. He presented his work in several international seminars and conferences. He developed good communication skills by participating in outreach activities and was very committed in his teaching tasks in the Université Paris-Saclay during the 3 years. For all these reasons, the jury awards the title of Doctor of Université Paris-Saclay to Mr. Raphaël Wicker. The jury encourages Mr. Raphaël Wicker to continue in this field of research.
So I will read the sermon du docteur. I don't know if I read it in French or English. Well, I go in English and then. So, in the presence of my peers, with the completion of my doctorate in astrophysics, in my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principle of research integrity. As I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationship to knowledge, in my methods, and in my results. Thank you. Quelques mots. J'ai jamais été ni très bavard ni très émotif, donc vous je vous avoue que je ne sais pas trop ce que je vais dire, mais premièrement, merci beaucoup, merci tout le monde, merci à ceux qui sont là. Je pense que je vais commencer par les gens que je vois dans mon champ direct de vision. Merci. Merci à mes amis d'avoir été là, ceux que j'ai rencontrés à la fac et ceux que j'ai rencontrés grâce à la communauté Discord de Angle Droit. Merci à mes collègues, merci à... je vois encore plein de collègues qui m'ont accompagné pendant toutes ces années, de la première à la dernière. 3 années très différentes où il s'est passé plein de choses, notamment beaucoup de fractures qui m'ont tenu éloigné du labo un certain temps, mais qui m'ont pas tenu éloigné de vous. Que dire de plus? Non, c'était un réel plaisir. Merci aussi à vous, mes très chers encadrants, d'avoir fait de moi un chercheur, d'avoir fait de moi une nouvelle personne. J'ai grandi avec vous. J'ai beaucoup grandi avec vous. Laura, I was your first student, and you did really a great job at it. Nabila, I mean, I don't know if je ne sais pas si je parle en anglais, mais Nabila, c'est toi qui m'as recueilli sur le palier de l'IAS quand j'étais en L3 et que j'étais vraiment désespéré de trouver un stage. Tu as recommencé en M2. Est-ce que c'était une bonne idée? Je ne sais pas. Mais voilà. Puis pendant ces 3 ans, chez toi, j'ai toujours pu trouver une oreille attentive. Quelques fois où j'avais beaucoup de choses à évacuer, j'ai toujours trouvé cette oreille chez toi. Marian, bon, bah, c'est grâce à toi que je suis qui je suis maintenant. On a beaucoup évolué main dans la main. J'aurai toujours de très bons souvenirs de cette conférence à La Réunion où je me suis baigné avec un plâtre, où on a regardé le France-Afrique du Sud seul dans l'hôtel avec personne. Et c'était vraiment des très bons souvenirs. Thank you to the members of the jury also for being here or remote, for reading the PA manuscript, for making comments, very useful comments, which I will use in the coming weeks, months, years, who knows, of my research. Thank you very much for being here and for allowing me to pursue my career as a doctor. Je vois tant de personnes. Merci à ma famille, quand même. Ce serait dommage de les oublier. Merci à ma famille de m'avoir soutenu et supporté pendant ces 3 ans, qui ont été jalonnés de bons moments, de moins bons moments, de plein de choses. Soutenus, qui sont là aujourd'hui. Certains ne sont pas là en présentiel, mais me voient devenir un grand à distance. Puis bon, bah merci à tous. Maintenant. Et merci à tous d'avoir été là. Moi maintenant, ma vie, ça va être la vie de jeune chômeur jusqu'à ce que je trouve un postdoc. Mais je vais en profiter aussi. Je vais beaucoup en profiter parce que certains le savent, mais je fais beaucoup de musique, donc ça va. Je vais en profiter pour encore plus de musique. Puis après, mon retour à la recherche, j'espère très bientôt. Et puisque j'ai réussi à ne pas encore pleurer, et Laura a réussi à ne pas encore pleurer, je propose qu'on ne tente pas notre chance plus loin et qu'on aille profiter des boissons et du repas au pot là-bas. Voilà. Merci. Thank you.
Congratulations. Yeah. Well, this is the only part I really want to be present live. I'm sorry.